Let's take a look at our Module 8 lecture here. Again, we're still looking at asphalt pavement and materials. In this particular module, or this lecture, we're going to take a look at stone matrix asphalt production and paving, inspection and quality control, asphalt concrete recycling, other asphalt surfaces, and of course, some test procedures. If we look at the stone matrix asphalt, or stone mastic asphalt, this has been used in Europe since the early 1990s. Over the years, many states and provinces within the North American area have introduced this concept into their roadway design applications and specifications. The differences between the usual asphalt mix and the stone matrix asphalt is the very high content of coarse aggregate particles used within the SMA design parameters. The coarse aggregate content value is around 70 to 80%. The results in loads being carried by friction between the coarse aggregate particles instead of by the binder and finder materials used within the mix. So again, we have creating a better surface area for the loads to be distributed instead of counting on the sand or the finer materials that are coated with the asphalt or petroleum product that we're using. So rutting resistance is greatly improved due to the strength based on the greater aggregate on aggregate contact surfaces by the hard cubical particles. And of course, the following table, which you'll see in the PowerPoint presentation, is a typical aggregate aggregation and quality requirements for this type of SMA mix. Pavement durability is enhanced by the rich mortar binder that is required for the stone matrix asphalt installation. Typical aggregate aggregation and quality requirements can be found, again, in the following tables that you'll see within the PowerPoint presentations. Hard cubical aggregate particles are required as the loads are carried by, again, aggregate to aggregate contact or stone to stone. Smaller amounts of fine aggregate would not supply enough fines under the 75 value in size to stiffen the mix requirements. With this in mind, 6 to 10% of the mineral filler comes from the screenings from the crushed rocks, is usually added to stiffen up the mix that we have. Mix design standards can be performed with either the SuperPave or the Marshall equipment, with compaction blow requirements set at 100 revolutions for the SuperPave test, at 50 hammer blows for the Marshall test, in order to limit the aggressive aggregate breakdown that might occur. The asphalt content used must be at least 5.5%, but it's usually 6% to ensure that there's a rich binder for durability. Drain down problems may occur with this rich asphalt content due to the fact that the hot binder flows down in the mix during the production process. In order to control this process, a cellulose about 0.3% or mineral fiber at about 0.5% is added to the binder as a stiffening agent. Polymers can also be added to the asphalt cement to also help in reducing down drain situations. Required properties of the mix usually include a minimum VMA of 17% and the maximum values for the voids in the coarse aggregate and drain down amounts. Voids in the coarse aggregate must be less than that obtained in a test of the aggregate alone. Voids are calculated from the mass of the coarse aggregate and the volume of the sample size. And again, we've already looked at this earlier in the chapters or the course, and we looked at how to calculate these void values. A preliminary test should be performed and a sample of the aggregate is compacted in a container by the dry rotted technique based on AA SHTO T19 procedures in order to determine the voids in the coarse aggregate or the VCA value. The mixed VCA should be less than the dry rotted VCA value obtained. Drain down sensitivity is measured by placing a sample of the mix in a wire basket on a plate in an oven and heated for an hour. The temperature should be expected plant temperature, with a second test being conducted at a temperature 15 degrees Celsius higher than what we have. Now, drain down, what we're looking at is we take the mix, we put it in the wire basket, we put it in the oven and we heat it. We're looking to see what falls out of the basket. So as the material falls out, this is what we know or is known as drain down. We can take a look at some typical mix requirements in the table below. And of course, these mix requirements usually result in stickier, thicker asphalt coatings on the particles. Of course, this helps improving the durability and resistance to cold factors. Of course, that contribute to the cracking. So we can look at the asphalt content, the air voids, the VMAs, and so on, and get that quality mix requirements from the table. Our SMA is about 20% more expensive than the standard mixes. So we got to keep that in mind when we're doing our design parameters, specifications, that we're going to have a cost factor that's going to be about 20% more. So we also want to keep in mind that the increased durability results in savings related to decreased maintenance costs and competitive cost alternatives that have pavement surfaces that are subjected to high volume and very heavy traffic or transport traffic. So again, we're looking at what are the cost factors, what's my return on investment. If I'm going to spend 20% more for this stone matrix asphalt, is it going to be worth it to me when I'm looking at the savings related to the maintenance cost associated with that same roadway? So one of the first authorities to use this type of alternative concrete asphalt mix was the province of Ontario, and has excellent results, or has had excellent results with this type of pavement surfaces. It has been found that the service life of the pavement surfaces has been extended by at least 5 years for high volume highway areas or road surfaces. Let's move on or move into the production and paving. So once we have an acceptable mix design ready and it's time to mix or the mix to be produced in an asphalt plant and placed and installed in an acceptable manner based on specification requirements, we now want to look at how we're going to go about this. So a traditional asphalt plant has 5 components that fall under the following. We look at the cold aggregate storage bins, we look at the dryer with the dust collection facilities, gradation unit or screens, hot storage bins, pug mill for mixing. So these are what we have in a traditional plant. The storage bin, of course, contains mixed asphalt, are often used as part of the asphalt plant operations to stone the asphalt materials until it can be discharged into the delivery trucks. Storage silos are also to store large volumes and keep a mix or mixture for a number of days without seriously altering its properties or contents. Heat is supplied to maintain the temperature, and oxygen must be removed from the silo and replaced with inert gas to prevent oxidation of the asphalt cement materials. Asphalt plants use 2 primary methods for measuring asphalt or the material into the pug mill for mixing as trucks are filled for paving applications. Let's look at a continuous plants. Continuous plants are the older method or version of mixing asphalt for different types of paving applications. Aggregates are fed continually into the pug mill and sprayed with asphalt cement and mixed and then placed into delivery trucks for transport to the work sites. The amount of aggregate for each hot bin is controlled by the gate opening, and the asphalt cement is pumped in at a rate that is calibrated according to the rate that the aggregate enters the pug mill. Batch plants are the more modern method of mixing asphalt materials for driveway and roadway surfaces. Asphalt and aggregate from the hot bins are weighed into the pug mill to form a mixed batch that we're going to have. The batch is mixed and discharged into delivery vehicles for transport to different job sites or road projects. Drum mixing plants are more economical for the production of asphalt cement are becoming more common in the industry. The steps in production are effectively reduced from 4 steps or the 4-step process consisting of a cold feed, drying, hot gradation, and mixing into 2-step process consisting of a cold feeding and dry mix. The steps are as follows. The cold bins store the aggregate and scales control the amount of material from each bin to ensure that the correct proportions are maintained within the overall process. The aggregate enters the drum with the burners located at the aggregate entrance rather than at the exit point in other types of asphalt mixing plants. As the aggregate enters the drum and proceeds through the process, the following occurs. The first thing is the burner assists in removing surface and free moisture. Very important. The second thing is the aggregate temperature is raised from 170 to 180 degrees Fahrenheit. When this happens, the asphalt cement is now introduced into the mix, and the aggregate operating temperature is raised from 180 to 200 degrees Fahrenheit, with additional moisture being driven off, allowing the asphalt to foam, trapping the dust particles and engulfing the aggregate materials. Mixing continues and the temperature is raised to the specific requirement indicated within the design specifications. The drum mixing quality control is simplified due to the fact that the proportions are continually controlled automatically in most plants that we have. The amount of aggregate entering the drum is recorded as the material flows over the conveyor belt and load cell. The amount of asphalt cement being introduced into the drum is automatically adjusted to correspond to the amount of aggregate. Moisture content of the aggregate must be measured to allow for a correction factor to be applied to the aggregate quantities entering the drum. The temperature of the mix leaving the drum is measured and the burner is automatically adjusted to achieve the required mix temperature. This temperature is normally lower than that required in a traditional asphalt production plant. Surge bins or silos are usually used with drum plants to allow for various rates of transportation of the mix and to help control possible segregation. Drum plants usually have higher production rates, up to about 5,000 tons per day, than the traditional plants. Let's take a look at some of the installation procedures and requirements. So after transportation to the construction site, the asphalt concrete must be laid finished by the asphalt paver and rolled to a desired thickness while maintaining the grade specifications indicated. The main aspects of the quality control measures are as follows. Of course, temperature. There must be a minimum temperature at the paver to ensure that the concrete can be compacted and that the aggregate particles can be worked into the requisite density to provide a strong structure. Next thing is compaction. The layer must be compacted to meet the specifications that is normally expressed as a percent of the laboratory density. Density is obtained from a sample removed from the pavement or by a nuclear densometer. Asphalt paving equipment and compaction equipment, of course, are shown in the PowerPoint presentation, so you can take a look at those. And of course, different types of compaction equipment were already described in Module 3. Inspection and quality control. The highway agencies, county or state personnel, or engineering firms will usually have inspectors at both the asphalt plant and the paving site for testing and quality control. The inspector at the asphalt plant must become familiar with the operation and controls governing mix proportions and temperatures. The following should be checked periodically each day. So we're looking at the aggregate stockpiles and cold feed controls. We're looking at gradation of the material in each hot bin and operation of the proportioning system. We want to look at the temperature of the aggregates, the asphalt, and the mixture being produced. We want to look at the operation of the dryer and mixer, and of course the quality of the mix in the delivery trucks. A visual examination of the finished mix can reveal any evidence of variations in the mix or poor mixing that is deviated from the design specifications. If the material forms peaks in the truck, the mix may be lean and contains too much fine aggregate or not enough asphalt binding material. If the mixture flattens out or is flat, it most likely has too much asphalt or too high a proportion of coarse aggregate blended materials. Samples are usually taken from the cold bins each day until it becomes apparent that the gradation is consistent with the design specifications. The cold bin gates must be checked to ensure that the correct combined gradation is delivered to the dryer for mixing. In many plants, the amount of material from each bin is controlled by scales or other weighing devices in order to ensure the consistency throughout the mix process. After leaving the dryer, the temperature of the aggregate are recorded along with the temperature of the incoming asphalt cement. The final mixture is normally recorded continually in modern plants to ensure quality control measures. Aggregates leaving the dryer is or are usually around 10 to 20 degrees Celsius hotter than the final mixture temperature that we want or have. Samples of the aggregates from the dryer may have to be tested periodically to ensure that all the moisture has been removed from the mixing process. Samples of the mixture produced are taken to make briquettes for the evaluation of strength, flow, and void properties. These samples are also used for traditional extraction tests to measure the asphalt content and the gradation of the aggregates blended materials. The test procedure uses a solvent to remove the asphalt cement, and we'll discuss this a little bit later on in the module lecture. If not, it'll be discussed in the PowerPoint presentation. So due to environmental concerns, the costly solvent is dangerous to use and results in significant disposal problems based on EPA and DEP regulations. The National Center for Asphalt Technology asphalt content furnace is used extensively to ascertain the asphalt content and produce samples for gradation testing based on the following procedures. The furnace ignites the asphalt by heating. The asphalt is burnt off with most of the emissions removed by a filter system. Large samples up to 5,000 grams can be tested. An internal scale continually monitors the sample to ascertain when the asphalt has been entirely removed. This process usually takes between 30 to 45 minutes. Contact must be maintained with the inspector at the paving site to discuss problems that might arise with the testing procedures. This is important because individuals involved with the overall mixing process want to coordinate remedial actions as quickly as possible when they are required to ensure that the mix or design mix meets design specifications. Let's take a look at some of the things we should be addressing at the paving site for inspections and quality control measures. At the paving site, the inspector should first check the prepared base and ensure that any weak or uneven spots are corrected before the paving process begins. Of course, very important, we've talked about this before, we want to make sure that we have a nice stable base, because once we pave over top of it, we're going to have some failure problems or concerns if we don't take care of it now. If an old pavement is being resurfaced, it is important that dirt and other contaminants be removed and cracks or weak areas repaired. Again, we want to make sure that that sub area that we're going to be putting our paving surface on is going to be ready to go. A leveling course may be needed in some locations to even out the surface areas. Often, a tack coat is specified to improve the adhesion between the layers or between the asphalt concrete and the base. The inspector should be familiar with the operation of the paver and the overall methods used to control the line and grade. Before starting paving each day, the previous pavement must be cut back to a vertical face in order to create smooth transition points between the surface areas that we're connecting together. The temperature of the mix delivered to the site is very important for effective compaction and must be checked often. And again, this is design specifications that are sent from the design professionals and the way they want this to be laid down over the course of the roadway surface. Samples should be taken for extraction and gradation tests. Nuclear gauges can also be used to determine asphalt content. Briquettes are usually made each day to evaluate the void properties and the stability of the asphalt mix. This is in addition to the similar samples being taken at the plant to ensure that the design specifications are being met at the plant and also at the site location. Compaction is tested by using a nuclear densometer or by coring samples out of the finished pavement product. The number of accepted tests suggested according to the AASHTO Construction Manual of Highway Design or Construction is as follows. Keep in mind, of course, this is used if there is no contractor process control in place to monitor the testing procedures. And basically what that means, again, the design professionals come through, they have a process control that they want to have followed. So if we don't have this, now we're looking at our construction manual for highway construction protocol. So the asphalt cement or the content of the asphalt cement should be 1 in 500 tons. Aggregate gradation, again, 1 in 500 tons. Void properties, 1 a day. Compaction, 5 a day. Superpave with various levels of control testing. Gyratory compaction control involves compacting samples in the field and measuring the density as a check on the consistency of the mix and any variations from the mix design. Gyratory compactor is portable, of course. Volumetric property controls requires testing the briquettes for void properties and composition. Tests include the following: asphalt content by extraction tests, nuclear gauges, or other tests. Aggregate gradation, aggregate quality including angularity, deleterious materials including clay and elongated particles, and of course we're looking at air voids, VMAs, and VFAs. Performance-based volumetric property controls involve measuring performance properties used in level 2 and 3 designs to ensure that the quality of the mix meets the requirements. Not all these tests can be completed in the field due to the equipment requirements. In situ pavement volumetric properties control requires the use of nuclear gauges or laboratory testing of core samples to ensure that the finished pavement has satisfactory binder and air void contents. And in situ means normal location. Let's take a look at asphalt concrete recycling. Reuse of materials in asphalt pavements is a growing trend due to the large increases in the cost of petroleum products and, to a lesser extent, the growing shortage of quality aggregates in some areas. Another important advantage is that the pavement defects can be rectified without an overlay and the resulting change in grade. This is very important or significant for urban streets. Recycling operations may be carried out by removal of the existing pavement to the plant, reprocessing and repaving, or by equipment which facilitates in-place removal, injuvenation, and paving, either as a cold mix or a hot mix. And you've probably seen remilling or milling machines out on a road surface where they peel up the top surface and then they'll do the repairs and then of course come in with a new surface over top. There are usually two main methods that are employed or used in reclaiming the existing pavement for removal. We have the conventional method that involves breaking up the pavement with a bulldozer equipped with ripper teeth or with a backhoe and loading and transporting to the plant where the material is crushed to the required size. And this is usually somewhere around 1.5 inches or less. In the cold milling method, the pavement is removed in small particles. The milling machine consists of a large rotating drum with teeth that cut into the pavement and remove it in chunks. The size of the particles obtained and the depth of the cut in the pavement can be adjusted as needed. Of course, the milling method is generally found to be superior, and I just mentioned that, and that's usually what we see out on roads when we're tearing up the top layer of the asphalt, milling that down to the layers that we need, and then, of course, collecting that and transporting it. The material can be removed to any depth and reduced to any size or the required sizes as needed. As I just mentioned, the depth removed can be varied to leave a surface that meets specifications for profile grade and transverse slope, thus correcting any rutting or surface irregularities in the pavement. In a traditional batch or continuous plant, usually up to about 50% reclaimed material can be used. It is usually added unheated to one of the hot bins that we have. The new aggregates are superheated and, when mixed with the reclaimed aggregate in the pug mill, raise its temperature to soften old asphalt cement and allow mixing of the old and new asphalt cement and coating or recoating of the aggregate particles. With the drum plants, mixes with up to about 70% reclaimed material can be produced. The new aggregate enters the drum at the burner and, as usual, and is rapidly heated. Reclaimed material is added usually about halfway along the drum and is heated by the new aggregate and by the hot gases from the burner. The new asphalt is added further along the drum and mixing is completed. Surge silos are important for all types of plants. The temperature of the reclaimed pavement materials continues to rise in the silo, softening the old asphalt cement for more uniform mixing of the old and new asphalt materials. Cold in place recycling steps usually involve the following steps. So first of all, the cold milling the existing pavement to a depth of around 2 to 4 inches with about 1 to 2% water often added to the milled material during this step. The second thing we're going to do is we're going to start to screen and crush the milled materials to reduce the maximum size to, again, about 1 to 1.5 inches. From this point, we're going to start the mixing with about 1.5 to 3% asphalt emulsion and a rejuvenating agent, often a light oil, to soften the old asphalt. From this point, we move on. We're going to start to relaying the material with the paving equipment and, of course, compaction. These pavements must be surfaced with a new wearing course after the emulsion has been allowed to cure, and we're looking at basically around a 2-week time frame. Cold in place recycled pavements are fairly economical, resist reflection cracking, and tend to mend themselves. Traffic interruptions is a minimal as the pavement can be reopened within about an hour of compaction. However, these pavements are recommended for roads with moderate traffic volumes only. Let's take a look at the hot in place recycling steps, and they will follow these procedures. So the first thing is we're going to have a preliminary we're going to remove all the patches, filled cracks, sealants, as they usually contain excessive amounts of asphalt. Next thing we're going to do is heat the pavement with infrared heaters. We're going to move on to scarcifying the softened pavement to a depth of about 1 to 2 inches. We're then going to lift the material into a mixer and adding a rejuvenating agent and other materials as required, and we're going to start to do the mixing. From this point, we're going to place and level out the material, and of course we're going to add an integral surface layer, a half to an inch thick of virgin material if necessary. These steps are completed in one pass of the paving train, or our paving machine that we normally see. Rollers follow the compaction. This type of construction is also a fairly economical method of pavement rehabilitation. It does not require a separate wearing course, repairs surface defects and cracks, and can be used on high volume highways, but it is not recommended for use where there is a danger of reflection cracking. Mixed design methods for plant mix recycling projects are the same as for new asphalt concrete, and we're looking to use the Marshall or the high beam methods. About 1.5 to 4% new asphalt is required. Of course, this is a significant savings from the 4 to 8% range usually contained in asphalt concrete from virgin materials. The new asphalt is 1 grade or more softer than the original. For example, we may get an AC5 instead of an AC10. The reclaimed asphalt is much harder than it was originally due to the aging. The resultant mixture should be close to the original design in grade of the asphalt cement. Other chemical rejuvenating agents or other types of asphalt such as emulsions or cutbacks can also be used in recycling projects. For in-place recycling methods, no universal accepted mixed design procedures exist, although construction guidelines have been established by many agencies. Other asphalt pavements can be classified as either surface treatments of various types of low-quality mixtures. The surface treatments are low-class surfaces in which an asphalt material is sprayed on the surface, then covered with aggregate. The aggregate either chips or sand are then rolled. A surface of about a ½ inch results. Additional layers may be placed on this built-up pavement structure as needed. Seal coats are a surface treatment whose primary purpose is to seal cracks in existing asphalt surfaces. A lot of times we see that on driveways. You know, we run over to the local Lowe's, Home Depot, hardware store, and we'll get a seal coat. And if you have an asphalt driveway, we'll put that down and we want to seal everything off. So dust is also controlled by this type of surface. Sand is usually the aggregate used in this type of application. Prime coats, also known as tack coats, consist of asphalt sprays on either an existing base of a Portland cement or a asphalt surface to help bond new construction to the old. Low quality mixes include those mixed either in a plant or on the road. Types, design, and quality controls vary greatly. Pavement surface defects such as rutting, cracking, or loss of skid resistance are being rectified using a new process called microsurfacing. Special equipment is used to lay a very thin, less than a ½ inch, remedial course on the surface. A select grade or sand aggregate is used with Portland cement, mineral filler, latex-based modifiers, and asphalt emulsions. Some test procedures that we would be looking at, and we did discuss some of these before. We can look at the Marshall, the stability, the briquettes, the asphalt absorption, the extraction test that we would have. Marshall briquettes are made for 2 reasons. One is we want to determine the void properties of the material. And the second thing is we want to test for the strength and flexibility in the Marshall stability apparatus. Aggregates are blended to meet specifications. A series of briquettes are made at a range of the asphalt contents. The briquettes are 4 inches in diameter and 2.5 inches high. After hardening, their mass is obtained in air. Then they are submerged to find their density for calculations of the void properties. The Marshall stability is used to measure the strength and flexibility of the asphalt mixes using the briquettes prepared by the Marshall method. Strength and flexibility are two important properties required of asphalt concrete for use in pavements. In the Marshall test, the prepared briquettes are heated to about 140 degrees Fahrenheit. This temperature represents the weakest condition for an asphalt pavement in use. This test measures the maximum load that the sample can carry when tested in compression, with the load applied to the circumference of the sample. This is the Marshall stability. Also measured at the same time is the change in diameter of the sample in the direction of the load application between the start of loading and the time of the maximum load. This change in diameter indicates the brittleness or flexibility of the mixture. Stability values are corrected to allow for variations from the standard 2.5 inch thickness. Asphalt absorption. To measure asphalt absorption by aggregates in an asphalt mixture, we got to remember aggregate is very porous, so this liquidy material is going to also want to get into those pores and suck into the aggregate. So the aggregate are very porous. Aggregate particle absorbs water in the surface pores. Asphalt, when mixed with the aggregate at high temperatures, is also very fluid and soaks into pores in aggregate particles. Asphalt that is in pores is not available to coat and cement aggregate particles. The asphalt remaining takes up less of the void space between the aggregate particles, thus coating more of the air voids. Let's take a look at the asphalt extraction test. And here we want to check the asphalt content and aggregate gradation of an asphalt mixture. Quality control of the asphalt pavement construction may require the checking of the asphalt content and, of course, the aggregate gradation. In this test, a sample is placed in a centrifuge. A solvent is added to dissolve the asphalt cement, and the solvent and the asphalt are thrown out of the sample through a filter by the centrifuge force. This concludes the Module 8 lecture on asphalt pavement and materials. And again, please take a look at the PowerPoint presentations to get a better understanding of the solved problems that will assist you with the homework and your submissions for our Module 8 course requirements.